Cole and an absolute genius on two legs. His name is Bowen Wang. He's just hydrating himself, so I'll give him a big round of applause for Mr. Bowen Wang.
Hello, hello. Oh, stuff not working. Oh, now works. Okay. Yes, thanks everyone for coming. I'll start talking about scaling and how why is needed for AI agents. Okay, so I think let's just start from. Okay, screen doesn't. Let's just start from the world that we're living in today. AI being like more and more powerful and more into our everyday life. And as a result, I think it's natural to project that in the next several years there will be more AI agents coming up, and they will be more integrated into our daily lives. You can imagine AI agents that do things like pay bills, manage your investments, making phone calls for you, and etc. So that's kind of the I think most people would agree with, like, what's going to happen in the next several years. Okay, but why do we need blockchain, right? How is it even relevant here? So I think there are mainly two aspects to this. One is that you need open financial layer that can that allows you to truly empower those autonomous AI agents. So if you look at the current financial system today, what is lacking is, let's say you want to actually receive funding, or you want to let's say manage the investment and so on. You often need to go through a KYC. For example, even if none of those things are happening, even if you just want to start a business or whatever, that's kind of a necessary step, and that doesn't work very well for AI agents. And what would work very well is this open and permissionless platform where you can just permissionlessly receive and manage assets. Another important aspect is that you need a settlement layer between all of those agents that's neutral and also open. So imagine if let's say we have billions or even trillions of agents, and everyone has tens of them. You need some way for them to kind of talk to each other, connect with each other, and potentially also settle agreements among each other. Maybe that's a trade, maybe it's a financial agreement, maybe it's a contract, something else. And you need a place that allows to do the settlement, and you need something that doesn't really bias towards some specific AI agents. And if you have a company behind that, it's likely going to be the case. Okay, so now that we talk about why blockchain is needed, why it's interesting for the proliferation of AI agents, I think it's important to examine what properties the blockchains we actually need. I think scalability here is extremely important because AI agents will be quite easy to create. There'll be some simple interface to create them, and as a result, there will be likely a ton of them. And if we don't have this very scalable infrastructure, then likely you'll run into some problem like congestion and degradation of the experience, and overall just won't be able to be the platform where trillions of agents can trade and settle and manage their assets. So yeah, what's unique about NEAR and why it plays an important role here? I think important thing is that we have this sharded blockchain design from the very beginning, and the throughput scales linearly with number of shards. So as more AI agents come on board, we can scale the blockchain by adding more shards to cater to that need. And something that's much less talked about is that we have this very interesting feature on the blockchain that allows you to pause a transaction in the middle and potentially do some off-chain computation, and then come back with the result of the computation and resume the same transaction. And you can imagine this is pretty good for AI use cases. For example, if you need to run some inference, do some database query, number crunching, analytics, you can do that in the same transaction and just pause it there, and then transaction comes back later and resume the same transaction to the end. With that said, I want to talk a bit about what we're trying to do for 2025. There are two main goals for scaling. One is 1 million transactions per second, and two is 200 millisecond blocks. Okay, let's start with, with the first one, 1 million TPS. So I want to first talk about like roughly how it's going to work. It just doesn't come out of nowhere. So the idea is that we have sharding from the beginning, and since we launched NYSE 2.0 last year, the system is fully sharded. So basically, if you add more shards, then you'll get more throughput, and you can roughly think of the throughput as the throughput of the number of shards times the throughput per shard. And we can imagine a world where we have 50 shards. Then if we have 20K TPS per shard, then that gives rise to roughly 1 million TPS. So what do we need to get there? So one thing we need is like actually to get to, let's say, 50 shards. So today we have 6 shards on mainnet. How do we get to 50 shards? So it's through this mechanism called resharding. So basically, this is a very effective, efficient way in the protocol to split one shard into 2 shards based on some boundary account. Right, so let's say we can, let's say we have a shard where it's includes all the account from Alice.near to Bob.near. To split into two shards, let's say we split, we determine somehow that the boundary is B.near, then the split can be from Alice.near to B.near, and then from B.near to Bob.near. And because of the stateless validation setup that we have today, we also need the resharding to finish in one block, so that it can actually, people can actually validate, validators can actually validate the state transition. So it's a pretty complex, heavy lifting, and I won't go into a lot of the technical details on how exactly that works. But suffice it to say that now we have this mechanism, and it's going to go out to mainnet next week. So in this release, we're going to split 2 of the shards and into 2. So we're going to increase from 6 shards on mainnet into 8 shards on mainnet. The release is going to happen next week. And then, so that's kind of the shard, how you get to many shards, but also that's not enough. You also need to, you also need each shard to be very performant as well. So there are a couple of important optimizations that we're working on. One is this optimistic runtime execution. So this is kind of to run the execution in parallel with the code that actually validates all the transactions are valid. Today they're run sequentially, and that actually just eats up a lot of time when you have, let's say, 10,000 transactions that all needs to be applied. And the other one is actually the parallel execution of transactions and receipt. So actually our runtime, because it's already asynchronous, all the receipts that touching different accounts can be parallelized without worrying about the outcome. So the order doesn't actually matter there. What matters is the order of receipts touching the same account. So we can leverage that and effectively parallelize our runtime. Okay, so let's move on to the next goal, which is 200 millisecond blocks. Just to give some background information on where we how we arrived to this goal. So when we released the NYSE 2.0 last year, we actually dramatically improved the single shard processing speed because we require all the node to run the chunk application to hold the state in memory. So when they apply a chunk, all the state is already loading to memory, so you don't have this performance problem where like some database reads might be super slow. So it already become much faster and also much more stable. We didn't change the block time at the time of the release because we want to see how it goes first, making sure that it's stable and everything works properly. So with a number of optimizations we've done since then, we are actually ready to reduce the block time. So we are actually working on this this release that's going to come after the release is going to go out next week. So that in that release, we'll reduce the block time to 400 milliseconds. And that's going to be a great improvement over today, which is about like 1.1 second. And it will bring a huge benefit to the entire ecosystem, meaning that all the applications running on NEAR will be much faster, and especially DeFi application because they often require multiple receipts, multiple hops, and that the effect will be very great improvement. Yeah, because of that, we'll have a sub-second finality as well, which is also very nice. And all of that's going to happen in April. But that's obviously not the end of it. So we're working on this bigger initiative called the separation of consensus and execution. So roughly what it means is that today we have, you produce a block and then people apply the block and then, the next block getting produced through consensus and then you apply that one. So the downside here is that the node are not constantly running the processing transaction. Sometimes they actually wait for a block to be produced. So it's like waiting there idle. So that's what we're trying to do in this big change is that basically we're trying to separate those two things. So what will happen is that consensus will run just separately. They'll constantly run just like all the transactions, and then the blocks are getting produced. And then separately, the execution try to catch up. From time to time, the chunk producer gets some blocks applied, and then they have the new state root, and they would actually submit this state root proposal from time to time on what the new state root may be. Yeah, this is kind of a overview of like how it works in the sharding setup. So this idea is actually not new. Like people have been working on the research related to this for a couple of years now, and there are some blockchains that have already adopted it. But no one has done this for a sharded blockchain. This is primarily because sharding is already very complex, and if you layer this on top of sharding, it's even more complex. And that's why even if you just look at this diagram, it'll probably be like, what am I actually looking at? It is quite complex, but luckily we already have the design fleshed out, and we're working on the implementation of this. So what this means is that it will give us two things. One is that the block will be even faster because we don't actually wait for execution. So that basically the only thing that you do there is just like all the transaction package them into blocks. So it will allow us to run to have a even faster block production time. That's where the 200 millisecond block time goal comes from. But also higher throughput because the nodes will be constantly executing transactions and receipts, and they're not actually wasting any time waiting for consensus to be achieved. So the throughput will be higher as well. And this is also one of the ways we will get throughput improvements for a single shard. Okay, so yeah, looking forward, we will hopefully by the end of this year, we'll have extremely fast and scalable chain, 200 millisecond block, 1 million transactions per second. And that will be a perfect settlement and financial layer for AI agents, however many they may be. So yeah, it's an exciting future to look forward to. And that's it. Thanks.
All right. Everyone? All right. There we go. Cool. So I'm going to be showing a lot of things today, and I've got a super long slot, so we're going to hang out for a little bit. All right. Not that. There we go. Cool. All right. Hey, everyone. My name is Kendall. I work on a company called Proximity that does a lot of research and development for the NEAR ecosystem. Just last week, we had a very exciting release we are calling Shade Agents. So the TLDR right there on the screen, these are truly autonomous, and we really do mean that, non-custodial, multi-chain agents. So agents are very hot right now, mainly outside of crypto, but even inside of crypto. These are just a few of the many projects that are launching different types of agents. On the Web2 side of things are moving very, very quickly. Probably some of the most exciting things you've seen is like the operator from OpenAI that can actually control your screen. We have Anthropic that has a similar type of product. Like they've developed an entire standard for how agents can interoperate together. But for the most part, they don't complete many actions for you because they really do struggle with authentication, payments in particular, and really anything that involves confidential information. So that's the Web2 side of things. On the Web3 side of things, most of these projects here are super exciting, but I would classify them as like frameworks. In the case of Arc, Eliza, etc., we have Virtuals up there. They're also a very cool project, but similar kind of a framework and then a launchpad. And then we have things like AIXBT, which has done an amazing job of I think, generating a ton of traction. It's like probably dominating mindshare more than just about any other entity on crypto Twitter. But it's mainly a Yap bot is how I describe it. I think Fresa in particular, that's the one with the green hair, is probably one of the more interesting experiments. They were also kind of just interacting with the agent, trying to talk to it, but you could actually try to extract money from it, which is kind of like a fun way to turn prompt injection into a game. So basically the TLDR and the way agents are today, they can get information really well. They can kind of get you to the point of taking an action, but generally they're not very good at actually taking that action. And there's a few reasons why. So, I mean, I think this is there's a couple of things that you need in order to have a truly autonomous agent. I think the most important end result is that they can actually complete any workflow for you end to end, which includes payments, includes actually going out into the world or the internet or wherever it is and doing something. But yeah, we're going to focus this mainly on how we can build autonomous agents in the Web3 space. And so these are some of the criteria of how you actually create an autonomous agent, like what you sort of need. The first one is probably something people don't think a lot about, but we actually think it's one of the most critical pieces, which is this idea of decentralized key management. What we mean by this is that agents are going to need some set of keys that they can interact with, but those keys actually need to be able to be interacted with by multiple instances of the agent. And the reason for this is that if you have a key that's too closely embedded into like where an agent is actually running, what that means is that if that agent fails for any reason, that key is lost, and thus any funds or any authentication that was dependent on that key is also lost. In crypto in particular, this is kind of the most fundamental piece, right? Is that like basically not your keys, not your crypto. So if you don't actually have persistent access to the key and authenticated access to the key, then everything that was a result of that key, which is literally everything you were doing in crypto, is lost. So we actually think that first piece is incredibly critical. Unfortunately, that's something we've been building in NEAR for quite some time now with a product we call Chain Signatures. Getting into some of these other ideas here. So we also think it's very important that you know exactly what your agent is supposed to be doing. And one of the easiest ways to do this, if you can, is you verify the code that's running. And ideally, you even verify the models that are going to be used to kind of perform some sort of action. So what we've been doing is working on ways that we can actually provide these guarantees as much as possible. And then getting into some other very important aspects, but kind of, I guess, further afield is like you do want uptime guarantees. The NEAR AI team launched a really interesting paper called Proof of Response. It's basically designed to solve this problem. We've been investing very heavily in this idea of trusted execution environments that are very good at verification, but they don't actually guarantee you uptime for any reason. And that's what Proof of Response is designed to resolve. And then some other things that I think are going to become best practices, but are still a bit nascent and new, is this idea of using smart contracts more as like guardrails for these models and these agents, rather than as like where you actually code the agent itself. I think realistically, given that agents require a lot of off-chain compute, they require a lot of access to off-chain data and state, you actually want to use smart contracts more to keep them on track and make sure like, hey, this agent is proposing to take this action. It's proposing to deposit my money into Aave. Well, I want to know that like Aave is not a good app. It's like somewhere that I want my money to be sent to. Like that basically we think smart contracts can be used very creatively to actually keep these agents doing the things they're supposed to be doing. And then last but not least, most of these agents, when they're acting on behalf of a single user, they should be kept as private as possible. At least the actions that they're taking, mean, the second you touch a blockchain, that's mitigated a bit, but like the decision process that goes into making that action, your personal data that might be a part of that decision-making process, all that should be kept private. And so what we did is like sought out to create a system that can give you those assurances. So yeah, basically what we call them is shade agents. We are convinced that these are currently the first truly autonomous agents because they actually hit each of those points. And we'll go through exactly how it works. So here you can see a diagram of basically the shade agent stack. There's actually two components that matter the most here. So the first, and you see this is like in that kind of trusted execution environment banner, is this worker agent. This is basically what you think of as like an agent. This is what most people are building when they're building an agent. Usually it accesses some, or like there's some wake up condition. Okay, agent's gonna run whatever that is, like someone requested, agent, go do this for me. Then there's some access to some data, some state, maybe that's information about the user, maybe that's information about like the price of a current cryptocurrency because it's going to decide to make a trade or not. And then finally, there's like some LLM or model, doesn't have to be an LLM, could be any sort of model where there's going to be basically like a decision-making process that'll be resolved. And then finally, once that decision is sort of finalized and the agent's like, okay, I want to take this action, then that action needs to be sent for execution somewhere. So that's the worker agent. That's running inside of this trusted execution environment, meaning that the actions that are taking inside of this environment are only known within the environment. There's no way to exfiltrate or no easy way to exfiltrate the data from here. And also it means that this code cannot be changed without basically wiping the whole environment. And thus, we'll talk about in a second why, like basically removing any of the information that's in there. The second major component is the smart contract. So we're using the smart contract for basically three main things, as you can see there. The first is to actually register this worker agent. What we mean by register is that this smart contract is going to require that this worker agent actually submits basically a proof of the code that it's running. This does this using kind of a primitive of a trusted execution environment, which is called an attestation quote. So basically what will happen is that the environment itself, in this case, like let's say an Intel CPU running this special environment, will actually generate a quote that shows the exact current state of this environment. So in our case, the most important thing it's going to be showing is the code hash of what's actually running in there. And then all of that is basically, it's signed by a key that's embedded within the hardware itself. And then that key is basically attested to by Intel in this case, who's saying, yes, that's actually one of our CPUs that we sold. We verified that like it should be, the integrity should be intact. And so the smart contract will actually take that quote. It'll confirm the signatures from Intel are valid. It'll confirm the signature from the hardware itself is valid. And then it'll actually extract that code hash and check that it matches the code hash that the developers of the smart contract, the deployer of the smart contract, set as like, this is valid worker code. And what this means is that anyone can actually spin up this worker agent on their own, assuming they have the right device, their own device, submit this quote to the smart contract, and then all of a sudden they're now a registered instance of a worker agent. This is important because what this means is that if any of these worker agents go offline, anybody else can spin up a new one, which gives you the resilience that's important for like actual autonomy. And then finally, what this smart contract is going to do, at least in what we think is the best practice, is if you take advantage of the feature we have, which is chain signatures, which TLDR is that a smart contract can sign transactions. Basically, we've given smart contracts keys via a decentralized multi-party computation network. Then the worker agent will do is actually request to send a transaction on behalf of this whole system. The smart contract will verify that the worker agent is registered, verify that the transaction they're requesting is one that makes sense, that fits some rules. And then they'll actually go out, sign the transaction using the smart contract's own key, and then finally send that to the network. And we'll actually walk through the code that shows how that works in a second. So yeah, here's kind of another flow of how the process works. So it's like step one, deploy the smart contract. Step two, anyone can deploy a worker agent. And there's a couple of like helper steps that we've created. Each worker agent will have a NEAR account because ultimately it's sending NEAR requests to the smart contract on NEAR in order to like send these transactions to the destination chain. So there's like a funding step. Then you also check like, is this worker agent registered? Because if it's not, you can call the smart contract, but you'll get rejected every time. So you have to complete that registration step. And then finally, you can actually then make requests to the smart contract to send transactions, and it'll approve these signatures, and then actually complete these actions for you. So how this is different from current T implementation. So it's become in vogue, I guess, to run crypto agents in a trusted execution environment because those are seen as at least better security than running it on just like some random hardware somewhere. The problem is that for the most part, these Ts they have a key that's embedded in them, and that's good for security because that means that someone else doesn't have that private key, and they're not misrepresenting that only the T can basically perform actions using this key. The problem though is that if anyone is able to pull the plug on this physical hardware, that key is lost forever. And that's important. That's a really important security feature, but it does mean that you can't actually trust that any of the funds you send to this key are always going to be there, which is like an insanely, it makes zero sense. Like we don't think that's like viable at all. I would not recommend you send your funds to any of these kind of agents. And so what we set out to fix with the Shade agent is that the worker agents are basically jointly able to use the same set of keys. So the keys are persistent, they'll always exist, but the only way you can actually request these keys to sign and do something is if you register and you prove that you're running the right code in the T. That's kind of the TLDR of this whole system. So here, we kind of show like how you can basically deploy one of these worker agents. It's actually pretty simple. If you use a product called Follow Cloud, they provide a really, really nice way to deploy these agents. So you can basically build your application, your worker agent using Docker. That'll generate a unique hash that is basically like the hash of the code that you're actually running. And then all you have to do is basically create this Docker compose.yaml and deploy that using Follow Cloud, and your worker agent will be up and running. And then here you can see actually the code of this is running in kind of our example worker agent. So what's happening here is we're generating a key within that trusted execution environment that will only ever exist in this instance. And the point of that is that if this worker agent goes offline, that key is lost, which is an important part of like the security properties of this thing. But you can then just spin up a new instance. You'll generate a new key. That's fine. You just have to re-register. That's all that means. And then here you can see we're actually getting the code hash of this, creating this attestation code, and then calling that register worker function on the smart contract, basically proving that within this instance of this worker agent, we're actually running the correct code. And here, so we built like basically a reference smart contract that actually implements some of these methods. So we've got two basically helper methods. One is this owner, just basically checking like, is there who's the owner of this smart contract? Who can update this code hash? In a best practice, this should either be immutable. You should just not actually have an owner, meaning the code hash can't be changed. Or, if you want your system to be able to be developed over time, this should be either like a DAO, or I guess like, worst case, like something like a multi-sig. And then we also have this kind of, you see that like method A, that's basically requiring that the caller of that method, which will ultimately result in a transaction, is running with a given code hash. And so one way you can actually use this is you can have different agents that perform different functions. They'll each have different code hashes, but then you can have like basically, maybe there's like 3 different types of agents you want to run in one system. They each have different code hashes, and you'll have different methods that will pertain to those different workers. So one worker might be able to like rebalance funds across lending protocols. One worker might be able to make trades. One worker might be able to update the whole system. And they can each basically be authorized to call different functions on the smart contract. Here's kind of just another way to sort of view that. Cool. So we're going to go through all that in more detail in just a minute here. But let's zoom out a little bit and talk about like, what can you build? Like, why is this interesting? So 4 major areas that we've identified. And I mean, frankly, this is probably just the beginning. I think actually one of the most interesting use cases for agents is taking a look at the DeFi apps that exist today, recognizing that just about all of them have a critical component of humans in the loop, and thinking about like, where can you actually remove some of those humans in the loop, or what new types of applications could you build if you could have some sort of intelligent decision making that could happen very rapidly, which is like one of the clearest advantages of something like AI versus having to like have this kind of slow, necessarily slow process of having humans in the loop. So it's like that's one really interesting way to think about like, imagine you could just replace a DAO with some agents, and where would that enable you to build? The other way to think about what you can do here is that because of the fact that we're running a lot of the core logic of this system in something like a trusted execution environment that can itself have sort of verified access to the internet, meaning you can call off-chain data providers. And I mean, at least know that that it's going to consistently call that route. You still have to trust that like URL is going to serve the right data. But basically, this enables you to more flexibly utilize off-chain data without having to like get an oracle spun up for specifically that purpose. And think about if you can act on this off-chain data, but then also utilize any type of model in order to make decisions. So we have a couple of example ideas there. We think like, a very basic one is just a lending optimizer, right? Where you can delegate effectively your funds to this agent. It'll then look for the best rates on a set of lending markets, and it'll rebalance your money across these over time as it notices that things are changing there. And then last but not least, I think like you can actually create interesting markets for basically anything that's digital. We've seen some experiments already where people are like letting you pay for a single use of an API key. So, I mean, a basic one could be OpenAI itself, right? Like you want to send a request, like a prompt to OpenAI's API and then get back some sort of response. You can actually create a protocol where you can basically delegate, anyone could delegate a single call and then have you pay them for that single call, which could get really interesting. Another area that we find pretty fun, and I'll actually zoom out and show you exactly how this works today, is this idea of a headless UI. So because these agents can be tracking interactions basically anywhere and then respond in a verified way, you can actually remove the idea of creating a new UI and like let people, for instance, interact with the application entirely through something like Twitter. So let's actually show how this can work because we built an example. All right, so we built this agent called Shade Agent 007. Basically what it does is it listens to any sort of request for its name. It then analyzes the body of the tweet and determines, is this throwing shade? Is this like a negative tweet? Is this saying something positive? And then it determines which token it's going to send to the user. And so right now we have the user including their account in there, but you can actually even get rid of that. So I'm going to send this tweet. I'm actually not sure whether it's going to frame this as based or shade, but let's find out. And it takes about a moment to respond. But yeah, so basically the idea here is that you can have any sort of existing interface where users are able to interact either directly with these agents or even just make any sort of comment. These agents can then see, okay, cool, there was a request that was basically effectively came to me. They're like, this user is trying to do something, and then it can perform an action on their behalf. So you could even have like an entire wallet that's built into x.com where you just could say like send X tokens to this address, and then the agent would be able to respond and actually like take that action and actually do something. Let's see if it's responded yet. All right, taking a little bit longer, so we'll come back to that one. And then last but not least is this idea of web markets. And so for this one, we actually worked with the UMA team to come up with initially a very basic demo, one that I think is pretty interesting, that can basically create user-generated markets. And these markets can be agent-settled, they could be agent-resolved, they could be agent-traded, and they can access any sort of public API or private web data. So we think this opens up like a lot of opportunities to basically trade based on digital information and digital information. All right, let's check back in on our bot and see if we've gotten a response yet. There we go. Cool. So it actually sent me these base tokens, and this is going to be on Hyperliquid. So let me, we'll come back to that one during the workshop. But basically, I'll show you guys that I actually received those tokens on the Hyperliquid mainnet. So basically what it did is this agent looked at this tweet, determined that this was a positive tweet. I guess it's harping more on the age of AI execution than on my comment about AI slop. And then it basically decided to send me these tokens to this address on Hyperliquid, which is pretty cool. So I welcome anybody to try it out. If you tweet at shadeagent007, include your address there and then say whatever you kind of want, and it should respond to you and actually send you some real tokens. They're technically soul-bound tokens. They cannot be transferred, but it's still pretty fun. You will be able to see them in your MetaMask wallet. All right, so now we can actually just go ahead and hop into a specific example. So we'll be walking through this template, and if you want to follow along, I recommend you go to nearai.ai/shade, and then you can actually just scroll down just a little bit, and you can see the template itself, and then we'll go ahead and walk through this code. But first, I'm going to show you guys what we built that uses the UMA optimistic oracle. So what's cool here is like you can actually see this URL, like this entire UI is being served from within this trusted execution environment. Generally, that's a bad idea because like you basically want to minimize any sort of access to this environment that you can. Ideally, you have this environment only calling into the smart contract, and that's one way rather than two-way. Otherwise, you do open up some attack vectors. But for the purposes of this, we figured we'd make it a bit simpler and actually have a UI that's still being served from here. So what we're going to do here is we're actually going to take some of the resolution criteria from a recently settled market on Polymarket. So we'll take this one. This is from, what is this here? It's the most passing yards on Championship Sunday. So this was all about a month ago, but never too late to kind of check out what's happening. So we'll go ahead and post this in here, and then I'm going to click submit. And then so we can see what's happening, I'm going to pull up the logs here. All right, let me check this environment. Let's do this. Cool. So you can see here, it's like checking a couple things like my balance, checking the key, making sure that I'm actually authenticated to call this method. And here you can see it's actually, this is the input of, okay, this is the market that we're aiming to resolve. And then you can see here, it's basically has now like authorized that I can call this transaction, that I'm able to actually send this signature. It's generated the signature here. This is going to be the address on Ethereum Sepolia that it's sending to. And then bam, it looks like we're sent. So where we can actually check this is on the UMA testnet page itself to see like, did this actually send? And let's see. It looks like this is ours right here. Yeah, this is our market will resolve according to whoever had the most passing yards. So we've actually now basically from here, yeah, we think we have a success. So from here, we basically said, okay, this is the market that we're looking to resolve. We entered that in. What happened then is that, we'll actually walk through this here. Let's walk through it. So this question came in here. Well, this is like us kind of making sure that we know which address to call. So basically this question came in. This is this question string. Then we passed it to Perplexity. Basically asked Perplexity like who had the most passing yards on Championship Sunday. Perplexity then searched the internet, used its LLMs, basically took probably, I guess, their like Google data plus their LLM and determined who had the most passing yards. And then we actually went and we like this is all in the worker agent. We generated this request to actually send to the contract saying like, hey, we determined we want to take this action. We're going to prove we're a verified agent where we have the right to basically call this smart contract. So here you can see us actually constructing the transaction. And yeah, so we're going to call this assert truth with defaults on the actual UMA contract. We're going to do this on Sepolia. And then here we actually put the transaction together. So we've got the address, the chain ID, the actual like transaction call itself. We generate this unsigned transaction request. And then this is where we actually call the NEAR contract, is with this like complete Ethereum transaction. So what we're actually going to do is we're going to send this transaction request, this unsigned transaction, to the NEAR smart contract. And we can actually look at the NEAR smart contract here. So we have this get signature function that's going to be being called with this this payload, which is that unsigned transaction. And then it's actually going to like basically call the chain signatures contract, which will then give us the signature back. And then once we have that signature back, we can reconstruct the transaction, like complete the transaction, and then send it to the Sepolia network. So we basically completed this loop of like worker agent that's going to be responding to these requests. That's running in this trusted execution environment. It registers with the NEAR smart contract, says I'm running this code hash, like this is verified code. This is only running with this in this trusted execution environment. The NEAR smart contract whitelist that agent so that agent can then send arbitrary transaction requests. And then what we just did is we sent that arbitrary transaction request that actually calling out to the UMA contract. So that's basically the flow of what actually happens. So now let's dive a little bit deeper into the structure of this repo so that you guys can kind of do this yourself. So as we said before, there's two main components. There's that worker agent and that smart contract. We'll look at the smart contract first because it's like a bit simpler. So basically in this contract, we've got just a couple of files here. So primarily we've got this live file. So you can see here we have an owner ID. We'll have these approved code hashes, and this is what initially the owner ID can basically add to. And again, in best practice, this is either immutable or managed by something like a DAO. And then we'll have these worker agents, these like registered worker agents. They can be registered by ID, and they'll also have like a mapping to a code hash. And you see here, yeah, we'll just initialize it. And then like the most important functions, even more so than their prior owner, is this require worker. So this require worker function, basically what this is going to do is this is going to tag a specific function as can only be called by a registered worker agent. And so what it's going to do is like check the account ID of anyone who calls this, and then determine like, are they basically in the approved list, and then like look at their code hash and say, okay, this worker agent is running this code hash. Does this match one of the whitelisted code hashes? And then here you can actually see the registration step itself. So this is what the worker agent will call when it's first getting set up. And you can see here, like we're actually picking a piece apart, the collateral they sent. This is basically that attestation quote from the trusted execution environment. And then we're going to actually call out to this collateral contract and run this verified check, which is basically looking at all of its signatures and making sure that they're valid from both the hardware, the hardware itself, and from, in this case, Intel, since we're using Intel TDX. So that's the contract. So basically, like for the most part, you guys can fork this contract, use it as is. The only thing you have to do is add additional methods here. Like I showed before on this UMA bot, is we had that kind of like basically the one to get the ECDSA signature. That's all you have to add, and then you're pretty much off and running. And then we can look at basically this worker agent, which is effectively the rest of the code base. So we set it up as like a Next.js app to make it really easy to handle this registration step, because like it is a bit involved. You have to generate this quote, you have to generate a key, and then you have to actually call the NEAR contract, and you have to like fund your account first. It's possible to do all of this through the CLI, but we just wanted to make it simple, so we put together this Next.js app. So you don't actually have to change too much. I'd say like you can mostly keep that part out of the box. What I recommend changing is if we go to the pages here, you're going to want to add routes to this API folder. Because basically right now it's just set up. This is just basically the registration logic, so it's not actually doing anything. But if you add, say, like another call here that actually does something interesting, and you add basically a file to this this API folder, then you can actually like perform an action. And so if we go look at my UMA example here, then I can show you the action that I added. So we'll go ahead and open up my code here. So you see here, like I added this UMA file here. I also added to this index, I added this handle question submit. That's basically that form field that I was using. And you can see that what happens when someone enters some data into that form field is I call this UMA API routes. And so here's where we're actually doing the kind of interesting stuff. So this main function here, this is what's called when you call that UMA route. So the first thing we're going to do, right, we're going to generate that the address. And so what we're doing here is we're actually determining what address we want to call from on the EVM side. And so this is basically like the way chain signatures works is each smart contract basically has a deterministic address. It can request transactions to be signed for. And so the inputs to that, there's basically a master public key of the MPC network itself. We have that in the docs. It's super simple to get. There'll be the actual account ID that you're calling from. So this is basically your account ID of your NEAR smart contract. A path, which is just an arbitrary string. The reason for this path is that you can basically control any number of addresses on a destination chain. And then finally, like the chain itself, like what type of chain. In this case, it's an EVM chain. So we're going to that here, but you can also do this for Bitcoin. Very soon you'll be able to do this for Solana and basically every other chain. And then, yeah, we basically, take the question string that was being asked and do what we were talking about before, calling Perplexity, getting the result from Perplexity, constructing a transaction, and then actually sending that transaction first to be signed, like verified and signed from the NEAR smart contract, and then finally to actually be relayed to Ethereum. And so the important thing to remember here is that you can actually do this for basically any chain. Right now, any ECDSA chain, any chain that supports ECDSA signatures, within the next few weeks, you'll be able to do this for any chain that supports ETHDSA signatures, which at that point means you can pretty much call any chain. So yeah, that's pretty much the structure of this project. So yeah, we'll probably have a little bit of time for questions, but I just want to make sure you guys have this link. So again, just this is the link to go to basically get the docs of how to build a shade agent and then get redirected to that repository. So that's going to be this near.ai/shade route. And yeah, that's pretty much it. I know I've been yapping for quite some time now. So yeah, if there's any questions, happy to dive into those. So we got at least like 10 or so minutes left. Sure thing, man. Yeah. We got another one right here.
Thank you. All right. You'll get some of your work up tomorrow, and then all of a sudden there's 1,000 shared agents, and they're all doing some really cool stuff that you want to see. What is that stuff that you want to see? If you can name like the top 3.
Yeah, I mean, I think the lower-hanging fruit is going to be managing assets on behalf of users in existing DeFi applications. So we'd love to see kind of like a lending rebalancing one. I think there's quite a few agents that are starting to do that now. But if they're not verified or are running just on a user's local machine, I think that's a bit dangerous. So I think you can even take some of the existing ones and just make them into shade agents that are interesting. But even better is that one of the unique things you can do here is you can build multi-chain rebalancers, since we already support from a single contract signing transactions for any chain. So I would basically take one of those lending rebalancers and rebalance between, say, Ethereum, Arbitrum, and Base to start. And then once we launch ETHDSA, you can add Solana, Sui, whatever other chains you want. So that would be one agent. I think we're really excited to see these kind of headless UI concepts. So one idea that was thrown out, and this is not legal advice because it is definitely a little spicier, but you can create kind of like a betting agent, sort of like a Twitter bet escrow agent. I mean, I'm sure everybody's, if you spend any time on crypto or Twitter, you've seen, somebody challenging somebody else to like bet on the price of Bitcoin in 3 months, and then they have to recruit Kobe to act as the escrow, which isn't really good for anyone. Well, with this, you can pretty easily, as long as you have clear resolution criteria, you can actually just create a bet escrow, give each of these users an address to send to. They could send the funds there, and then once the date passes, like the end result of the bet passes, then the bet will just automatically resolve and send the money to whoever the winner is, and these users don't have to do anything. And like all they have to do is interact with Twitter and then send funds to these addresses. They don't have to interact with any UI. And so this is just a basic concept, but it can be extended to anything. And then last but not least, I think this is actually like, I don't have the specific idea here, but this is a way to build kind of a true 0-person company where like you can actually have just these agents that sort of act on their own behalf and either funneling funds into a DAO or even just to themselves. And I think what this does add is this layer of trustlessness where, I mean, I haven't even thought of what the business ideas are, but there's definitely an opportunity to think about like, where is trust absolutely imperative? Where do we not even really want humans in the loop? We just want code, and then go out and build that system. I think this is like really one of the first times you can actually do that in a much broader way. Like smart contracts gave us a bit of that, but we only have a small number of truly trust minimized smart contracts. It's basically Uniswap. And that's like kind of one of the only ones. There's been a couple of other experiments, but they're pretty light. So I think this like really opens up the design space for those types of applications.
All right, thank you. Anyone else?
All right, thanks everyone. Appreciate it.
So what time do you want to break?
All right, ladies and gentlemen, there is plenty of coffee to go around for everybody over there. There's some scran, there's food, there's cheese. I think that they might be putting something a little bit different on pretty soon as well. There's iced tea, there's lemonade, there's water if you want to stay extra healthy. There are clothes and swag and pins and jumpers, etc. out there, so please go and get them because we need to give them away. We will be back here at 2:10. That is 2:10 for the Americans. So keep an eye on the clock where we will have some heavy hitters, including the co-founder of NEAR, Illia Polosukhin. So catch you then. Hold on one second. All right. Okay. Here we go. 1, 2, 3, 4, 5, 6. Witness. Hooray. 1trillionends.com. All right. Ladies and gentlemen, I know that the food is delicious and the coffee is even sweeter, but we are about to welcome our very next guest, our next speaker. Did that rhyme? I think it did. If not, I will let you enjoy the wonderful Alex Shevchenko to talk about all things NEAR intent. So please do give him a big round of applause.
Okay. Okay, hello everyone. My name is Alex Shevchenko. I'm the CEO of Department of NEAR Efficiency. I'm the guy who is together with Bowen making sure that NEAR protocol is working. And we're going to talk today about NEAR intents. Maybe some of you have been already hearing about this protocol and actually using it. Raise your hands if you did. Okay, that's great. So lots of people who already tried it. And as always, I would like to start with some kind of citation from a great person that I really admire. And today, this is the one. There are 2 infinities in the world, the size of the universe and the number of AI agents that will be launched. And I'm not 100% sure about the universe. This is what Einstein said approximately 100 years ago. And that's actually, I think this is actually the truth. And like many people, like there were already a couple of talks mentioning AI and agents. And I would like to start with, a basic and a basis here. So what is an AI agent, right? So this is a system that is able to perceive the environment. It is able to process this information. Then it is able to take actions towards some specific goals that are set. And then it is able also to learn within this process, right? So this is something that we probably, understand already. Now, it is very easy to envision a future when these AI agents, the systems that are trying to achieve their goals, they have different goals, right? So some of the systems are helping you to get food deliveries. Other systems are helping you with the transportation. Some other systems are helping you to swap tokens. And because of this, it is very easy to see the future where we are not going to have just a single AI agent that is going to help us out, but rather we're going to have a multitude of them, right? Trillions, right? And that's actually the case. And if so, then they are going to have their own specialization. They are going to be experts in some domains. And in order to provide good services to the users who are going to use these agents, they probably would need to have a place to cooperate. If my AI agent knows everything about myself, then maybe it is not very specialized in the food delivery that I like. And then maybe it needs to cooperate with other AI agent who is specialized in it. So the cooperation between the agencies is a very, very important thing. They need to discover each other. They need to negotiate in between themselves to figure out the deal, who is going to pay whom, or how it is going to be structured. They need to settle this deal. And in case there are some problems with the delivery of the services, they also need to raise dispute cases, and these disputes need to be resolved, right? This is like a thing that actually need to exist. And the truth is we are building it, right? And this is a NEAR intent, and this is a grand vision behind the NEAR intents. So this is the protocol that contains an off-chain message bus for communication and discovery of the AI agents. This is a new type of action on the NEAR protocol that is specifically existing in order to settle these negotiated parameters of the deals in between the AI agents. And then there is a payment channel standard that is connected to it. There is also a dispute resolution mechanism that is built in this thing. So everything that I'm talking about up until this point is pretty generic and pretty forward-looking, right? Just because AI agents, they are making their baby steps right now. And in order for such a system to mature, it is going to take years. But what we can do right now? Well, we actually can do a multi-chain DEX right now. And this multi-chain DEX is something that gives you a first very simple type of an intent that people want to do. And also, this is a use case that works in crypto right now, right? But if you would think of it, it is not very far from the general protocol that I was talking about a couple of slides ago. People, in order to trade multi-chain, they need to discover a counterparty with which they need to trade. They need to negotiate about the price of the asset, and they need to settle it somehow. So the actual exchange of the tokens need to happen. The only thing that is not existent on the multi-chain DEX is the dispute resolution mechanism, because the amounts of the tokens are tracked on the blockchain. So the smart contract can be a dispute resolution point that there will be no disputes, because the smart contract is able to check the amounts that have been traded, right? So in fact, multi-chain DEX, though it sounds very different from the AI protocol, or AI agents protocol, it is actually not very far from that. And that's why this use case is a great first use case for the wider vision that we see for the future. And it is live. You are able to try it out on near-intents.org. It is in the beta stage at the moment, so please be careful with your money and stuff like that. Make sure that you are not you are able to deposit there the things that you're able to lose. Now, what we have right now with NEAR intents in comparison to what we have been talking about on Redacted conference just 3 months ago. We do have lots of chains that are already integrated with the protocol. We are adding these chains rapidly. So we now have Bitcoin, Solana, Ethereum, NEAR, Base, Arbitrum, Ripple, Doge, Zcash, Bera, all of the Aurora virtual chains that are launched right now. They are all integrated with NEAR intents, which are more than 70 virtual chains that are available. And more chains are coming soon. The list of the integration, we are slowly starting to run out of chains for integration, just because almost all of them are integrated, right? NEAR, Solana, and Ethereum wallets are supported, so you're able to log in with any of these wallets inside of the front end of the intents, and you're able to execute transactions with this protocol, which is also pretty great. You don't need to have a NEAR account in order to transact on intents. Multiple partners have already integrated the protocol directly into their front ends because it is an open protocol. Anyone is able to do. You don't need to go directly to near-intents.org in order to use the protocol. That's good. And even more integrations are coming. We have a natural more than 500,000 daily volume, and it is steady growing. We have seen the volume of swapping exceeding several million US dollars daily trading volume already on this protocol. But like every single day, there is more than 500K in comparison. And this is like in 3 months, right? So 3 months ago, there was 0. And now we have not been running any, marketing campaigns around it. We were not dropping people tokens, anything. People just started to use it because they see the value when they're able to permissionlessly or trustlessly transact across chains. And we have more than 50 tokens that are listed there, but all of the major tokens that usually people are trading on centralized exchanges, and I'm talking about stable coins, base tokens of the corresponding chains, all of these tokens are there available. And the thing that I can tell you is that already right now you can drop using your centralized exchange, and instead of it, go and use NEAR intents. Now, obviously, I would not be me if I would not bring something new here to share with you. And I'm glad that I am able to do this, and all of this happening because of my tremendous team that is just building all the time. And there are a couple of things here, and the first one is the support of passkeys. Now, you're able to log in NEAR intents in the protocol and in the front end directly with the passkey. You even don't need to have a crypto wallet anymore in order to non-custodially store crypto that is located on different chains. It is live right now. You're able to go there, log in with the passkey, and here you go. You have your crypto there, and you're able to swap it and do whatever you want to do. There is not a single transaction that the user is sending. The only thing that user is doing is signing the messages, and it is able to do with the passkey cryptography, which is different from the NEAR cryptography that is used, but it is working like that. So that's the first thing. Yeah, and the best thing, I encourage everyone to try it out, because what it gives to you also is the walletless experience, where there is no switch of the interface from the dApp to the wallet in order to sign something. You're completely staying in the dApp, and it makes things so much simpler, and that the flow is just straightforward. So I encourage everyone to try it out. And there is a second feature, which is the OTC trades. You can think of it as a peer-to-peer trading, where instead of trading with the market makers that are providing liquidity inside of the protocol, you can trade with your buddy. You can create a trade in which you specify the amount of tokens that you're selling and the amount of tokens that you're getting back. And you can send it as a link to your friend or to the counterparty with which you're willing to trade. And then this counterparty is able to click it, and it is able, and this person is able to countersign the trade, and then it is going to be settled. So there is a true peer-to-peer trading. Why this is important? For people who are caring about with whom they are trading, like institutions, they now able to trade only with selected partners because they have passed KYC or like KYB or something like this. So all of these available in the near-intents.org right now. And together on top of this feature, in the following days, we are going to release a functionality of link drops. And this is functionality that is even better. Or like this is an additional step. This is a kind of a sub use case behind the OTC, where you're able to put inside of a link drop, you can say that I would like to transfer 10 USDC to the person who is going to redeem this link drop. And then you can send this link to your mom, and she is able to click it, log in with the passkey, get 10 USDC, swap 5 of it into Bitcoin, swap 2 of it into Zcash, keep the rest of it for herself, and then obviously sell everything into Aurora and hold it forever. But that's actually the thing that you're able to do. She doesn't need to install a crypto wallet. It is going to work like that. It is going to work like magic with her face or her finger signing all of the requests. From my personal opinion, as a person who was always pushing towards the better user experience, this is the way how things should work, because this is how Web2 is working right now. I'm getting my Revolut account or my bank account. I'm just looking at my phone. I'm sending money to somebody else, and then they are receiving this money. This is natural. It is not natural when I need to switch to some kind of wallets and do some complicated things, right? So this is how things can work in crypto. And the most important thing, I would like to put an emphasis here. This part is like this front end. It is an open source front end. It is just a reference implementation for the front end. What we would like to see is different protocols, different distribution channels, different wallets to incorporate this solution directly inside of their front ends, so that their users are going to see absolutely the same user experience, while they don't need to switch into other, applications into their browser in order to perform such a straightforward and simple action as just swapping tokens. So I encourage everyone to do this, especially if you have a distribution channel. We do have lots of partners that are in the process of integration of the near intents, and all of them are loving it. So in the following months, you're going to see quite a number of big announcements around these things. So my mom uses near intents with passkeys, so why aren't you? Thank you. And besides the talk, we actually have the an additional kind of live coding or like a demo thing. I'm not going to do the coding, but I'm going to show you one interesting thing, how AI agents are able and are actually working today with near intents. And I would like to give a big shout out here to Vadim from Near AI, who has been actually building this AI agent that I'm going to show you, and he's the mastermind behind it. I'm just kind of stealing a little bit of his fame and showing this to all of you, but credit everything to him. So what I'm going to show you is an AI agent. I'm going to make it super large. An AI agent that is available right now at app.near.ai. You can go there. There is a section around the agents. And the agent is called DeFi. How do you read this? I still didn't figure out how to read this, but let's call it DeFi. And this agent, what it is able to do, I'm not sure whether the reason there. The description is, as you can see, as as usual in the alpha projects, this is an alpha version of it, but this is an agent who is able to accept your money in the form of USDC on the NEAR blockchain. It is able to analyze the crypto trends based on the price data from the CoinGecko. It is able to make a decision in which tokens to invest. And it does this investment through the NEAR intents. It holds this portfolio of tokens for a certain amount of time. And then at one day, for example, it liquidates this position and sends you back this money. Literally what this AI agent is, it is a tool for anyone to invest in crypto without a knowledge of anything of crypto. It's like if you're a type of person who is buying, you know, lottery tickets or something like that, you can do it like that. Probably there will be at some point in time several different profiles how you can invest more into riskier assets, invest more into more stable assets, right, and stuff like that. But this is something that you can do already right now. This AI agent has obviously quite a lot of source files, but let's check it. So there is by the way, all of this is just written in Python, so it can work as an ordinary Python code. I know that the most hyped part about NEAR is TEEs. So you can put this AI agent inside of the trusted execution environment so that it becomes a non-custodial, or like a shade agent that Kendall was launching just last week. So this can work as a shade agent. And it has the part for the analysis of the trend. So as you can see here, there is a crypto list of some particular tokens that are listed on the NEAR intents, and this agent is trading these tokens. What you're able to do is to actually update the trends, and this logic is working through getting the information from the CoinGecko API. So this is a function that is called get investment recommendation, and but like inside of it, it's a little bit down there, but there is a fetch real-time data. So actually, this agent is fetching data from the CoinGecko, right? You can open it. It's fully open source and fully available. Now, once it gets the information, and by the way, this agent is running this evaluation on its own. Once per hour or something like this. Then what it has is the part that actually interacting with intents, right? So this is a code that Vadim needed to write in order to make sure that this program, this bot, is able to execute respective transactions within the NEAR intent protocol. And if you're going to go into this stuff, you're going to see some things that are very specific to the NEAR intents, right? So this is the RPC, this is the endpoint where you're able to get the prices of the tokens. There is an information about, some specific messages, how the intents protocol is working, then these messages are getting signed. You're able to, this is the thing that is actually happening. You're just, this is a function that creates a message that should be signed, and like there is a generation of nonces. There are some different functions that are able to encode and decode data, like all of the typical things that you expect out of the code that is working with the normal blockchain at the moment, right? So, for example, this is how the payload is created, right, for the intents. Yeah, serialization data, all of this stuff. There is a separate function for withdrawing of the intents, right? So, and like all of the typical things. And the last thing that I would like to show to you, probably nothing. I don't want to show you anything in the code. You can check it out. But I've tried it yesterday. And at the moment, back then I tried it from the console, from the terminal. I'm going to show you the actual transactions that were happening. We're going to see it on NEAR blockchain. But the intention for this agent is to be able to be invoked directly from Twitter. And actually today, Vadim was showing how he was invoking an investment out of crypto by just mentioning GNear AI, which is the AI bot that is existing in the NEAR protocol. So check out his Twitter account. It is Zacodil, Zacodil, and his latest tweet there, or one of the latest tweets there. So he was actually invoking this AI agent there. But for the sake of just demonstrating you how things have been happening, so this is actually my terminal. This is what I hope you see at least a little bit. I can make it a little bit bigger. So this is actually the call that I was executing, and as you can see, there was a transaction which is a transfer of the USDC token. This strange token on NEAR is USDC. So I was transferring 10 USDC. Probably this was just one USDC. 1, 2, 3, 4, 5. Yeah, this was just one USDC. There was a second transaction to invoke it with 10 USDC. Yeah, this is it. So this transaction, I was transferring 10 USDC to this agent, to this smart contract. This is not an agent, this is a smart contract, defi.gnearai.near. And I was, together with this transfer, I was adding a message that I am depositing on behalf of a Twitter ID, which is mine Twitter ID. And this is exactly how things are going to work with the integration with Twitter, right? So I have been depositing this, and then this transaction was executed. You can see here that this is a transaction. There is like a key, whatever the things, and inside of the logs, you are able to see that that here was emitted an event that actually started to run the agent. And so what happened in this transaction is that this smart contract accepted my deposit. And this, you can think of this smart contract as a vault where the money of all of the users who are using this AI agent are held, because AI agent has a kind of hotkey, and in case it is broken, right, then you can withdraw the money from the agent itself. So it's much better to have a smart contract where you are storing the data and storing the money. They are parked there instead of an agent that has a hotkey. So I was depositing money inside of this smart contract, and this smart contract was transferring this money into the AI agent. So for that, AI agent is able to use Intense protocol in order to purchase the position for me. So we are able to find this transaction. This is actually this transaction on NEAR blocks. And as you can see, I was transferring, I was transferring this 10 USDC into DeFi, right? And if we're going to see the, if you're going to look at the execution, yeah, actually these are the logs that were invoked there. What this agent did afterwards, it was pushing several transactions onto NEAR Intense in order to take this 10 USDC, deposit inside of the NEAR Intense protocol, and purchase tokens. This particular transaction, unfortunately, was not including any split of the tokens in between different assets, because yesterday the market was going down. All of the assets were performing worse than Bitcoin, so that my AI agent decided that the most wise thing to do would be to invest in Bitcoin only. But this was what the AI agent figured out only from the data from the coin market cap. Oh, sorry, from the CoinGecko, right? And actually, what I was able to do is check my capital position, right? So the agent was kind of creating a position for me. And this position, as you can see here, was that it was 106 Satoshis because the token was only Bitcoin. So the agent in the end decided to purchase only Bitcoin for me and returned these sats back into this smart contract as I was describing earlier. And hopefully today I'm going to receive my Bitcoin back. It is going to automatically, it was set for as just a single day. It is going to automatically sell the Satoshis back into USDC and automatically return it to my account. And this is how you're able to do, how you're able to create interactions in between the AI agents and NEAR Intense protocol right here, right now. So the actual vision that I was sharing with you, making sure that the AI agents are able to communicate, they're able to interact with some kind of additional services, and are able to find counterparties to execute particular things. And in this case, they were market makers who were providing liquidity and creating markets inside of the NEAR Intense. That was a counterparty for this AI agent. Now, this thing is actually fully working right now, maybe within a little bit limited use case at the moment, but we are on the road to build and incorporate much more use cases in the future. Follow Vadim for additional updates on this stuff. I think it is super cool. Already today, we are able to invoke it from Twitter. And I didn't test it yet, but I'm going to try it out. And if you are willing to build your own AI agent, go check the near.ai and figure out all of the stack that is available there. There are lots of things that are available there. And you can build use cases like this right away, just writing some Python code. So thanks, everyone.
Take questions, Alex?
Questions?
Questions? I have a question, Alex. I have a question. When can we expect more liquidity on Intense?
So probably not everyone have these massive bags as David has. So at the moment on NEAR Intense, you're able to swap $1 million of Bitcoin in $1 million worth of NEAR, Solana, or stables. Unfortunately, we cannot serve David, but for everybody, for all of the normies who are swapping kind of within this amount, you are already able to do it.
Good, great stuff. Thank you. Questions from anyone else? All right. Thank you, Alex.
Okay, thanks you.
Good stuff, as always. As always, one of my favorites in the whole wide world. Look, give us like 5-10 minutes max. We're going to get the boss mic'd up, and then he's going to come here. He's going to do a live whiteboard session, and he's going to school us about all things AI agents. So it is Illia Polosukhin up next. Sit tight.
Excuses right now either, right? Because I'm running everything.
Correct. Yeah, we could. I guess we could plan for it. So all they have to do is literally lift the button.
One, two, three, 1, 2, 3. Thank you, ladies and gentlemen. Our last talk of the day for 1 trillion agents. Before we take some time to relax, we open up a happy hour. You can get as drunk as you want, but don't forget you need to be here tomorrow as well. The co-founder of NEAR Protocol, Illia Polosukhin, is about to join us on stage for a solo talk talking about the future of agentic commerce before, and you're very lucky that you get to experience this, he dives into a live whiteboard session. So please, for one last time today, put your hands together for Illia Polosukhin.
Okay, well, I hope everyone who made it here have had a great time at Denver, and you know, keeping it at 1,600 meters high, but not too high. Cool. So I want to talk about future of agentic commerce, kind of introduce the idea, and give you some of the demos as an update from what we presented at Redacted. So one of the kind of main stories that I've been talking about probably for the past year and a half is that AI is this final platform shift, right? We're transitioning from what effectively became our norm, right, with mobile apps and applications and websites, to really this new plane where AI becomes your interface to internet, to services and goods, to really each other, right? Like that's the change. And just as a side note, movie Her was set in 2025, so we're kind of living it now. And the important part here is that as this is happening, more and more of who you are going to be facilitated by that AI, right? And right now, these AIs are provided by different companies, and those companies always will have kind of their own profit, their own value kind of first. And so the idea that we've introduced over a year ago have been user-owned AI. Is really, how do we bring AI in such a way that it is on your side? It's not really trying to maximize revenue and profit for some company, but actually maximizes your individual well-being and your individual economic success, right? This really builds up on kind of user-owned internet, maintaining full ownership of your data, assets, and power of choice that we've been always talking about as NEAR, but also adding this idea that AI will be your universal interface. And through that interface, it needs to really be the facilitator and also, firewall in many ways of how you interact with internet, right? How you interact with computing and global market. And this needs to be built in such a way that everybody can benefit from, right? Economically, the developers who build this, the services who participate in this ecosystem, and the users, right, if they're willing to share their data and kind of want to receive something in return. So that's kind of user-owned AI. We've been kind of introducing different parts of the stack. It's not, as simple like, cool, it's done. It's really required a ton of work from the whole ecosystem. Now, one of the concepts we introduced at Redacted have been this idea of an assistant, right? Something that, you traditionally associate maybe with ChatGPT, but the thing is, like, ChatGPT doesn't really do things for you, right? It usually responds, it gives information. They added like few different features, but it's mostly just an informational kind of plane. But we envision this assistant to be really able to act on your behalf in Web 2 and Web 3, right? It has all the context about you and being able to, kind of sometimes even pick actions directly, sometimes surface it to you depending on kind of complexity. But also it's able to now make decisions and, scavenge the earth and the internet to find the right choice, right option for you, right? So meaning it'll connect directly to other AI assistants, to other agents that are, representing services and that are representing other people. So one of the points that, if you've been here a year ago, I've been talking about chain abstraction, right? And for crypto, that's probably one of the main pain points. Like, there's a ton of chains, more chains launched over the past year. There's a ton of kind of different applications now everywhere, and becoming harder and harder to use all of this. And so chain abstraction, we've been kind of introducing this idea since the end of 23 to really allow everyone to use in a straightforward way all of these applications and all of these chains. And there's a ton of teams in the NEAR ecosystem have done tremendous progress. I mean, Hod was just talking with Peter, is showing more and more exciting things there. But the kind of next step beyond that, right, is going to be AI as a final chain abstraction. It's going to be effectively on your behalf executing different actions across different chains, across different applications, and you will not even know sometimes like the details of that because it doesn't really matter, right? That's kind of, you come to the talks to learn what is going to happen in a year, right? So this is kind of the idea. This is where the whole space is going to be going. So just to give you like a visual example, right? Your assistant effectively on the background will be, doing different actions, right? I was, planning to come here, so it, we'll be finding what is the best, when to buy the tickets for me for the travel. On the background, it's, I like metal concerts, so finding the metal concert as soon as it opens up, buy the ticket for it, and rebalance my stablecoin in different borrowing markets based on different APIs as they're changing. Right? Again, you don't need to go and manually change this. You don't even need to do it through wallet, where it's now easier to kind of chain abstraction. But actually, it will just do it on you on behalf because it knows that's the action you would take if it was yourself. So that's kind of the idea, kind of where we're going. Right? It's a number of agents effectively on the back end working on your behalf, executing different actions, and your assistant coordinating this and really, surfacing all of this and augmenting it with your context. So what do we need to do to actually enable this future, right? Well, if you've seen any of my presentations, there's always a stack. So this is the stack to enable that. First and foremost, we need to make sure that all of this is confidential and secure, right? Effectively, right now, when you're using any of the AI models, right, you're giving all your data to some company, which may or may not handle it very carefully. There's have been leaks, and people have access to other people's data and different AI assistants. And importantly, as is you putting more and more of your context, right? Maybe this is your medical records, your banking information, so you can actually do automatic taxes. Maybe it is actually listening to every second of your life, because now that's a full context to enable the best predictions. Well, you don't want that to be owned by anyone. You don't want it to go to anywhere, right? So it's extremely important that this is all fully confidential and every single action is secured. Now, as this kind of agentic network, growing, it needs to have a hosting platform where all these agents will live. We need a way to share the data, share the kind of user information, so different agents can interact on this, and your AI assistant is able to really leverage it. You need to have a way for your assistant to find what are the agents out there, so agent discovery. And finally, all those agents, they are, as we said, importantly making money, so there needs to be a payment system. So one of the things we've been working on is so-called decentralized confidential machine learning cloud, right? So this is, if you've seen my Twitter, I talk about TEs a lot. This is the idea that we can actually run the machine learning models, like the LLM models, as well as any other model, inside the secure enclave, the trusted execution environment, in such a way that you have very little overhead on the execution, and everything is end-to-end confidential, right? Not person who runs the hardware, not developers, not the model builder are able to access what happens inside this confidential VM. And so around this, you can build a whole cloud where you have confidential VMs with GPUs and without, that actually can run agent code, that runs inference on different models. And all of this is end-to-end encrypted. You need kind of on-chain payments and registry to coordinate all this. And all of this kind of enables this confidentiality. I'm not going to go too much into this because it's a agent commerce talk, but this is kind of one of the fundamental blocks to enable this. Now, agent hosting we introduced at Redacted, and since then we've launched a few hackathons, which people kind of continuously building more agents. Really exciting to see over 475 agents now built here. Obviously, there's a lot of example agents. Is now platform that builds agents itself, and this is actually the think of this as your application store, right? Where each agent is a kind of some capability or new information or a new way to use your user's data to execute things, right? This can be anything from a product manager agent to an agent that helps you with shopping. So if you haven't seen it, go to AppNet NEAR and AI. There's a way to create agents, and this kind of platform continues to evolve. So every agent here will be hosted inside secure enclaves, and so you're able to kind of interact and transact with them in a privacy way. Now, what we're releasing today is a agent interaction and transaction protocol. So this is kind of the protocol to enable agents to actually not just talk to each other, and not just call tools, but support payments, support transactions, support exchanging information, right? And this is extensible standard, right? This is kind of a new way, think of this as HTTP, which enables agents now to communicate to each other in a structured way. And it has kind of capabilities as extensions. You can introduce new ones as a developer. And again, think of them as headers in HTTP for developers in the room, where you can keep adding more functionality to it and leveraging it for a structured interaction between agents. It also supports not just one-on-one agent. You can have a whole group of agents talking together in one effectively chat group and interacting. They can add new agents into this thread and kind of provide you a whole host of kind of capabilities to really create this kind of future where agents are now doing things in the background and you are not really directly interacting with this. So this is pretty abstract, I realize, and so is many of my talks. And let's see if we can get a demo going. Cool. So this is a demo. There's a way to play it. Okay. I guess. All right. So this is a demo where, first of all, you can check out the specific agent we're going to use, which is SoundSage. It's an expert in buying audio equipment. And so it's deployed already on the kind of agent hosting platform. And now you're going to actually not directly talk to it. You don't even maybe know it exists. Instead, you're talking to your assistant, right? This is the assistant that will navigate all of your kind of internet applications and agent needs. And so you go and you say, hey, I want to shop for green headphones. It itself has some information already, right? It's it's an AI model. It has context. It can actually fetch data potentially from other places. And so it gives you a quick response from that, but you can say like, no, I actually want some cheaper headphones. And so what happens here, you see this like two. We'll scroll through this, but there was the message effectively a subthread created where a SoundSage agent was called, and then the SoundSage agent replied back with a whole selection of products to choose from. And so users selected them, and then as like added pretty much initiated buy flow, which asks them for address where to send it. Again, this was communicated as a SoundSage agent, and you get effectively a payment request. And so this payment request, asking for $11, which you can now pay with your kind of Meteor wallet with your stablecoins. This itself will effectively pay the agent, which will receive this money. And then the agent itself will go and use Amazon API to actually ship you the headphones. And you get an order ID that you can now track. And so this conversation itself, right, is an example of kind of AITP interaction, where some of this was a natural language, some of this was a structured data, right, specific information to select from products, payment requests, information exchange for address. And all of that was actually done by your assistant in a subthread with the agent, where you just kind of interacting directly with your assistant. Again, you don't even know there is another agent involved. We kind of show those subthreads only in the developer side. On kind of user side, you will not even see that. So that's kind of the experience that we're going after, right? Where your assistant effectively can go now and find specific agents who have specific skills, talk to them, inform them maybe with some of your context, with information that you have. If we actually go to next, can we go back to slides? Yeah. So so like you as a user, you go to your assistant. Your assistant then, using your memory, can either respond directly, maybe can use some other tools, or can go to a discovery agent and ask it, which agents would be useful to reply to this request. Discovery agent itself has an index of all agents that are hosted in the platform. We also want to have actually a federated model where other agents as well will be contributed to this index. And in this discovery agent effectively says, hey, SoundSage and this shopping assistant are useful agents for this request. Let me add them to this thread with the user, right, and kind of remove myself. And so then those agents can now reply with structured information, with maybe clarifying questions, maybe with request for payment or any other kind of interaction. Like this agents can be effectively your rebalancing lending market agent that now runs every hour to rebalance your portfolio, right? This can be any agent now can run, and your assistant is kind of coordinating them. So that's the idea of kind of AITP to really interconnect all of these agents, and then discovery to help find where are specialized agents in the ecosystem. So to kind of link it back, all of this, built on top of all of the blockchain infrastructure we've been building at NEAR, right? Obviously, I mean, if you've been here before, you've heard from Bowen to continue scaling the blockchain, really to enable it to handle more and more payment requests, more and more inter-chain requests, agents that have their hosting. We have shade agents where like you have smart contract and the kind of this TE hosting platform interacting together. We have a chain abstraction tech, which is a combination of chain signatures and intents to really enable this kind of really simple interaction. For example, you got onboarded on Base with USDC, and you want to pay for something that's in Solana, right? All of that gets completely abstracted out. You don't even need to think about this. And finally, the TE infrastructure that I talked about, this cloud that really enables to run effectively anything in verifiable, confidential way, but specifically machine learning AI loads. So that's kind of like a multi-purpose, protocol that we've been building with NEAR over past, years to really enable this vision and really interconnect these pieces. And we're going to do a whiteboard to actually explain how all of this fits. Now, it's not just kind of NEAR AI building this. There's a ton of teams building, like some of them are here contributing. There's a lot more partners as well that didn't fit on a slide. So really exciting to see kind of all of this community coming together and building. Now, I just want to finish on this last thought, which is this is kind of a massive shift in how everything is done in your life, right? Like you go from, hey, I have, dozens of apps that I'm using, my credit cards everywhere, to really this kind of platform shift that enables, among other things, to kind of really power everything with crypto rails, but importantly, to transition to effectively a single interface that's on your side. That's not trying, again, you go to google.com, google.com is trying to make money off you, right? You're the product, you're not the user. The users are advertisers. And so this is kind of the platform shift we see. And that itself, right now, that economy itself is a $1 trillion of kind of a year of business opportunity to really transition into kind of this new AI commerce and user-owned internet. So I'm really excited. We're making progress. There's a ton of pieces kind of coming together. It's been a lot of kind of building out these protocols and systems to enable this. But we are now this kind of in production. We have this, first agents really making real actions in the world. We have partnerships coming together to enable this. So really exciting. Stay tuned. Stay for the whiteboard to explain how some of the tech works. Thank you. You wanna? Well, I don't think we've tried this before, right? I guess, long time ago.
First time.
Yeah.
At least as far as I know.
Yeah. I think Alex did once with Justin Drake, like with a smaller group. But
Okay.
yeah, this is, let's just say, first time we're doing a live whiteboard. So, that said, we always do them without preparation anyway, and in not one take. So this is not that different.
Yeah.
But if you have questions, raise a hand and we can dive in. So today we wanted to just go over kind of the tech stack we're building, because it's kind of getting more and more complex as there's more and more moving pieces, which are also built by different teams, and like all of the different teams contributing effectively into like one master stack that we're trying to enable with this vision. But yeah, would be good to actually have like all of this outlined, and yeah, if there's any additional questions, we can cover them. So I'll just draw the stack, and then we can kind of go line by line. So actually, something that long time ago, when we started NEAR blockchain, we were trying to figure out how to do networking stack, and we've implemented a version of it. But one of the challenges generally with blockchain has been there's no incentives on a networking level, right? You're kind of hoping somebody will give you data, and there's no kind of way to identify if somebody did not give you data.
Or to punish.
Or to punish, yeah, if they didn't give you data. And so one of the protocols we actually released last week, it's called proof of response. And so it's a new primitive that really enables a way to prove when somebody is not responding to you, to everybody else. So then obviously we have, the blockchain itself. We have the chain signatures. I'll actually put the TEs here before intents.
Yeah, sure. This is the T cloud.
Yeah, TE cloud.
Yeah.
We have intents. And then we have AITP. And I mean, there's more things, but let's just kind of focus on these. So all of them kind of using stuff underneath, or planning to use, or kind of depend on what's built. But also there's kind of maybe indirect dependencies. So maybe let's start with proof of response, right? So one of the, again, as I stated, the problem been, okay, I'm Alice, right? And I want to get some data, a very simple, question from another node. And that node doesn't respond to me, which can be it's offline, or it just decided that it doesn't want to respond to me. And traditionally, there's literally no way to prove to anybody else that this is happening. And so the question was like, why this is important? Let's start with this. Well, if this node stores your data, right? So let's imagine this is a data storage protocol like on Machina, right? And that node like stores your data. There's a proof on chain that it stored your data. But then when you actually go and reach out to it, it doesn't give you the response. It doesn't give you the data. Like there's no way to tell to the network that like, hey, this node is not doing this. Now, for our agentic internet, it's even more important because this node can be running some agent, right? And this agent maybe even have some private data or access to, some APIs. And so, again, if you depend on this agent for your, for interactions, like this is agent that rebalances your portfolio and it doesn't reply, you need at least find some alternative. And ideally also find a crypto economic way to punish it. So what kind of proof response introduces is a network of relayer nodes which are interconnected, and so with service nodes as well. And on each edge in this network, there is some effectively latency and cost. And so when I'm joining the network, right, as Alice, I now specify a path. So let's say I'm trying to retrieve some data that I want my request to take. And I'm paying a little bit. So there's a payment channel established. I'm paying a little bit for this request. So what are different cases, right? One case, this replies back, and the information goes back to Alice. She's happy. She paid a little bit for the networking. Now we have a networking protocol for incentivizing actually information exchange. Now it's possible that this node, let's say Bob, is doesn't want to reply to Alice, and for example, it didn't actually store the data. And in this case, again, two options. One is it replies with just an empty response, right? Like, hey, there is a reply. And so Alice, but because it's a cryptographically signed reply, Alice can then show to the network, hey, Bob replied me with nothing for this request. This is a malicious behavior. The other option is he just ignores, right, and doesn't reply. And so in this case, the intermediate nodes now are by protocol effectively either break the edge themselves with this node, or if they don't do it, somebody else will break the edge with them, right? So the idea here is that if somebody in this network is not replying, right, that can be because of the node somewhere on the path is not replying. There is a edge broken. Now, edge breaking is not like that bad because it effectively means one connection is broken. There's a little bit of penalty from the
But here you're assuming like all the nodes on the path are following the protocol, but like it's possible, or like at least one node is following the protocol.
At least one node is following the protocol. Yes.
But what if they all not following the protocol?
Yeah. So we'll get to that. We have the semi-magical solution for some of this. But yeah, at least one node is following the protocol. You effectively get a broken edge propagated back to Alice. And the idea that like if Bob loses all the edges, that's effectively a slashable condition, because that means that like everybody who is communicating to it, it's not replying to them, right? So as more, obviously like initially Bob has a lot of edges, and then Alice can continue, asking on different paths. And if Bob is really, adamant on not replying to Alice, it will end up effectively losing all the edges with all the related nodes, and in turn getting slashed, and effectively, in turn proving that it's not replying.
But you need to prove that it has lost all its edges.
Yeah. So the cool thing is we have a blockchain, and the blockchain, like all of this doesn't work without some way to post all of this topography information somewhere, right? Because like all of this right now is, if you don't have a blockchain, it's just a partially observed information for each node. Now, the cool thing is we do have a blockchain where all of these edges are actually recorded as payment channels. And so every time you open up a connection, you establish a payment channel on chain as well. And so you have a full topology recorded in a smart contract. And so now when, this condition happens, then the slashing happens on chain as well. And the Bob loses some on-chain stake that they have. So this is on one side, this itself is a networking stack, but on the other side, it does use blockchain as a, this global settlement layer, which is what blockchain is really good at. Now, the cool thing is then blockchain can use proof of response to effectively maintain its own networking connections, because now, again, if validators, for example, not replying to the data requests, they can get slashed not just for like malicious block production, but now also for not being available for data requests, which is what data availability and all the other things are trying to ensure.
Is there a protocol on how much they should stake?
So that is, up to an application and kind of how it's used. I think for blockchain, the cool thing obviously is the validator is already staking, so we can reuse that.
Yes.
For things like up the stack, where obviously it's going to be some economic research that we'll need to do. Cool. So this is again, it's a new primitive, like on the on a kind of level of like proof of stake, enabling networking, incentivization, and verification. Do you want to talk a little bit more about blockchain parts?
Yeah, has been talked about a lot, including in different whiteboard sessions. What should we talk about? Obviously we can talk about the general stuff. So basically, we have those blocks, and we have a shards, and each block contains chunks from different shards. And important thing is that there's only one chain, makes a lot of things simpler. And how the chunks gets verified. So since the release, Nightshade 2.0 release last year, is that now like on each block, so there's this like rotation of validators happening. So on each block for every shard, there's a random assignment of validator to shards. So they validate the state transition of that given shard in that block by verifying the state witness. So the witness basically is like a kind of a data that says the state, and then proof. So state is basically the state that you touch during the execution, and then proof is proof that the state is actually valid. It does belong to the state root. So today this is a Merkle proof. But the nice thing about it is that it doesn't have to be Merkle proof. Any proof that proves a state belongs to the state root would work. So for example, in the future, we can replace that with zero knowledge proof, and they'll be much smaller, and enable us to have better scalability. Okay, so I guess we can also talk about the runtime.
Well, I think the interesting thing that we haven't talked much in previous whiteboards is decoupling execution from consensus.
Yes. Okay, that is. Raise this.
So yeah, for context, Bowen introduced that at Redacted.
Talk about it
Okay.
at the presentation today.
Okay.
But not in a lot of detail.
Yeah.
Because it's very complex. So it is kind of like something that's kind of already complex on its own. Like things like consensus, they're by nature complex. But when you like add sharding to it, it just become like complexity squared. So okay. Let's look at this. So today, how it works is like, okay, you have block you produce, and like everyone go and process block, including like applying the chunks and whatever. And then they're basically like done here. Like here, they're just like basically like they wait here. I mean, assuming let's say like a block's pretty empty, right? It takes like very little time to apply. They wait here until the next block is produced according to consensus, right? So what actually happens here is that the block producer is sending approvals to the next block producer approving this block. And then the guy, after receiving all the approvals, now he has all the approvals to produce the next block. But there's just this delay, right? So during this period of time, the node is basically doing nothing. Kind of like, I mean, obviously there's network connection going on. It's like sending messages to different nodes, but it's not spending any of its CPU time actually doing the bulk of the work, which is like applying transaction and receipt, right? So if you think about what the blockchain is, it's just like this machine that continuously take like new transactions and apply them and get the new state. But here it's actually not doing that job. It just there's just this delay here that's idle, and people have realized that this kind of sucks, meaning that we're not fully utilizing the power of every node. So instead, what we do is that we say, well, we want to better utilize this entire thing. So basically, it's split into consensus and execution. So in this new paradigm, we still produce blocks this way. It's just that the difference is here is that after a previous block is produced, you don't actually wait for the blocks to be applied and for the new state roots to be updated. You just like go immediately to the next block, trying to reach consensus on what the block is. So what that actually means is that it's basically like every chunk producer producing some chunk which package the transaction there, and they send to the block producer. They send the header to the block producer, and the block producer produce a block. And by doing this, it's basically just like a way to agree on what the transaction for like all of the shards are. They basically just like ordering and packaging transactions, and this just like goes on and on. And separately, there's like execution, which is like trying to catch up. So let's say we have let's say we get everything to work very well. We produce block every 200 milliseconds. So this chain would move forward. And then on execution, basically you're saying like you do the kind of what we do today, which is like you take a block, you look at the, let's say each shard, look at the chunk, and then try to apply it. And at some point, this is configurable, but at some point you're done with applying some chunks. You can say, okay, I want to submit this state proposal. So on what basically this is like, this is roughly state root after block H. So basically this proposal says, here is the state root after applying this block. And it submits this proposal, and then it gathers this endorsement from the validators by doing the same stateless validation that we do. And then if it has enough endorsement, then it can be included in a block, which is part of the consensus chain. But there you're only validating that it has enough endorsement. So that's to certify the state root has been updated. So this way, the node is constantly doing work on like applying transaction and receipt and update the state. And you get better throughput this way. Another thing that is, I think, somewhat unique about this approach in the sharded setup is that generally with sharding, if you want to have low block time, it's somewhat incompatible with a lot of shards, because the more shards you have, the larger the variance will be between like receiving the chunks. So if you have that, if you have to wait for every block to be applied, then it's more likely for some chunks to be missed. But here, it address that problem, because one, you don't actually need every single block to include a chunk from some shard, because it's kind of asynchronous between consensus and execution. But also that because you don't actually apply it here, so it's much easier for like everyone to like keep up with the pace and actually produce a chunk that contains the transaction. So it also nicely solves that problem.
The other interesting thing is, so right now in NEAR, you have effectively a limit, like one transaction here can only execute for like 200 milliseconds. And that's partially because, I mean, even before we're reducing block time, like you need to give enough time to kind of between execution and starting to produce the next block. And so here, if you decouple this, right now, it doesn't matter how long the transaction actually takes. Like you can, you just order.
Yeah, have longer running transaction just get updated later.
Yeah, and so things like Aurora, where sometimes like on EVM and Ethereum, the transaction actually take can take 5 seconds to actually execute of real like crunch time, right? You can actually now apply this, and it can actually take whatever. On NEAR, it will probably take like 3 seconds. But yeah, so you can actually have like longer running transactions on top of already all the other stuff we have with a sync, right, where you can do other things. So it's really kind of improving fundamentally how like reducing latency, increasing bandwidth, and in turn also increasing what type of transactions you can do, which has already been like pretty powerful in there.
Sorry, hopefully you can hear me. If I start a transaction. So if I start a transaction, like you were just saying, that may take 2 seconds, and your block resolution time is faster than it took me to execute, and I was using data based on a block that is finalized at the start of the execution, is there a method of getting the delta state changes from the blocks that may resolve in between the start and the end of the execution? Did that make sense?
So the idea here is like the transactions are queuing up, right? So you can think of this like the consensus part is just feeding the queue of transactions. So like every time the block is produced, it just puts things into a queue, and then this execution just takes in a queue. So if there's other transactions touching the same state, the same contracts, they'll just go into a queue and they'll start executing after. So to give you an example, like let's say there's like Aurora transaction 1, and then it will like start executing Aurora transaction 2. Now, because NEAR is parallel, you can have like ref executing here.
Yep.
You can have some NFT minted in parallel as well. But on the same contract level, which is kind of our level of parallelization right now, you will have them sequenced. And so they'll just go into queue and wait.
Yeah.
Yeah. So indeed, really cool. I mean,
Yeah, it's really nice.
solves a lot of interesting things for NEAR, but also kind of pretty innovative across the ecosystem. So let's go to chain signatures.
Yep. So this is, I guess, also connect with TE. So basically, so what this thing is that let's say you have an account, or let's just say smart contract. So it can be a regular account as well, right? So this is a smart contract on NEAR. So today, just like regular smart contract, and just the thing you can do is within the NEAR ecosystem, right? But what this chain signature allows you to do is that now it suddenly have addresses on, let's say, Bitcoin, on Ethereum, on Solana, and let's say Base. So this smart contract itself has a count that it controls on all of those chains. It's a very interesting paradigm, because now what it can do is literally you can have some logic that allows it to sign transactions for each of those chains. And then some relayer can go and take the transaction and go and execute on those chains. So it enables a lot of interesting use cases, especially in like cross-chain DeFi. Like for example, if you want to like bridge like some token from like one chain to another chain, historically the way you do it is like you prove that something happened on one chain, and then you go and send the proof on the other chain. The other chain verify, okay, there's a proof, and then it like does token minting or like unlocking. But here, like what it can do is literally like it can just like release. Let's say it has this address on Bitcoin and it holds on Bitcoin. It can sign this transaction and release Bitcoin or like send Bitcoin from that address to some other address directly. And this is both easier to maintain because you don't need to worry about this complex logic of verifying between chains, but also it's actually faster because like a native transaction is sent. The latency is basically the latency of that chain, of the destination chain. So this is more like from kind of the use case perspective, and NEAR intents, for example, is a big use case of chain signatures, and in general, like there are people building multi-chain lending, borrowing, multi-chain asset management. You can have like one contract that implements some like DeFi strategy that manages accounts on all sorts of different chains and does like rebalancing. That can even be controlled by like AI agents. I can talk about that. Yeah, so a lot of cool stuff can be done from this primitive. Should I talk about how it works?
Maybe briefly, yeah.
Yeah.
Like the final state or current final state.
Yeah. So like roughly there's some set of nodes. So it's like MPC nodes. So each of those nodes roughly they hold a key share. And then the key share doesn't. So you need a threshold. There's a threshold. You need a threshold number of them to participate in a signing request in order to generate a signature. And the signing request happens on NEAR. So there's like a NEAR. It actually runs a NEAR node that indexes the chain. And when a signing request is triggered, it verifies that it's actually a correct signature request by that's just smart contract logic, but here it's to verify the state transition is correct. So no one is trying to maliciously attack by generating a bogus request. And then after it got the request, it started the threshold signing process, which is the threshold cryptography that I won't get into. But then in the end, the signature is produced and then submit back into the blockchain. And the interesting thing here is that we want this MPC node to also run inside TE to make sure that the key share can never leak. So generally, the problem with MPC is that it doesn't have a good defense against the long-range attack, meaning that if some old set of participants collude, they can still recover the root key, and then everything is screwed. So inside TE, like you have basically you only allow the key share to be held in unencrypted form inside the TE, and when it needs to be persisted, encrypted by the TE's encryption key, so that even if the node operator is malicious, there's no way they can get it out. So it makes it much more secure.
Yeah, so maybe that's a good transition to TEs,
Yep.
right? So I kind of mentioned this in my talk as well, but just like on a high level, we have the hardware, like for example, a CPU, and so there is a specific way where you can actually run a full operating system image inside this secure enclave in such a way that kind of processes outside, so this is secure enclave, trusted execution environment, processes outside are not able to access it, right? So traditionally, TEs have been kind of considered A, very hard to use, and B, very insecure because of two reasons. One was that the way to run software inside them required to actually write in a special way using very specific API. So previously it was Intel SGX. It effectively required to rewrite everything in C. It had very low level APIs. It didn't have, for example, parallel instructions like SSE. And so it was very limiting what you can do with it. Plus, there was a lot of known side channel attacks and how to actually extract information from it. Now, since about like March or April last year, there's a new kind of generation of trusted execution environments. With Intel, it's called TDX, Trusted Domain Execution. There's a version for ARM. There's a version for AMD. And so those allow to actually run a full operating system image inside this environment. And so you can literally prepare, think of it as Docker. You can spin it up there. And now what you can get, which is really interesting, is that when some computation is done, you get effectively a certificate that this computation was done on this data. And importantly, only this computation was done. There was no other computation done on this data, which is really important for a lot of the use cases we just talked about, right? Because if you think of the MPC that Bowen described, well, you want to know that only the calculations that you asked MPC to do was done and nothing else, right? It didn't try to extract the key,
Yep.
didn't do anything with it, and actually maybe even deleted it so that this shard is not even valid anymore going forward because it doesn't exist. Similar with proof of response, right? This ensures that nodes actually following the protocol in the whole network of the nodes that following the TE. So there's a kind of this concept of quote which TE can return. And so on top of this primitive, right, there there's a few different bits and pieces that are being built to enable this. So first of all, there's kind of reproducible Docker builds that especially File Network been pioneering on how to make it really easy to distribute software in verifiable way. So you actually get effectively you can upload a specific Docker container, which the hash of which is known and it's consistent, and so you can actually look at source code, verify that the source code is not doing anything malicious, reproduce the Docker, compute the hash, and when you do some computation, it actually proves to you that this hash of a Docker is running inside TE. Right, so that's kind of basic primitive. You get this Docker container was run inside TE on this execution, and only this thing was done. Now, kind of what this allows to do, Kendall was talking about, is the concept of shade agents, right? Where now you can actually call, for example, some execution, and then go back to the blockchain, right, and post that, hey, these calculations were done on this data, and this is the outcome, right? And so your smart contract can effectively receive outcome, verify on chain that this, quote is correct, that you actually have indeed used this, done this execution inside TE on this data, only this thing was done, and this is the outcome. And now this outcome can be used somewhere in smart contract. To give you an example, you want to build this rebalancing portfolio. You have the chain signatures to hold assets on all chains, but who does rebalancing, right? Like, what is the logic of rebalancing? Well, you can actually run arbitrary computation. For example, go read Twitter, fetch data from Kaido, decide on a new allocation in the index, and then return back this new allocation, right? And then, maybe it does like some cross checks on a smart contract level, and then verifies that indeed, let's execute that rebalance.
Yeah, I think the important thing here is to know is that there is a way to verify this attestation without going to Intel server. Basically, there's a database that they publish that can be put on chain, the database of certificate that can be put on chain, and then that can be used to verify the attestation, which is what shade agents do.
Yeah. And similarly, like if you are our proverbial Alice who wants to do some computation off chain, right? She can connect to this node through TLS, so through encrypted connection. So this node exposes effectively, it's a certificate proving that it runs on the same Docker. And so then you can, encrypting with this, with a certificate, communicate some private data that, again, this node, let's say this is our semi-malicious Bob, cannot see whatever the data coming in, what happens inside. So some computation is done, and then the response comes back, again, with this quote, right? So now you have a full end-to-end confidential, effectively computation done on remote server, and you know that only this computation was done. For example, it removed all the data afterwards. It didn't save it. You know that it ran exactly as this AI model or this AI agent, and you get back kind of certificate that the answer is this, right? So this enables effectively both on-chain and off-chain actors kind of communicating with this TE node to really do confidential computation in off-chain case or verifiable in the on-chain case. But this is like a single node, right? So okay, what happens when there's like lots of these nodes? How do you actually manage this? Well, this is where proof of response comes in, right? Because the reality is like there might be some node, and when I say like this is any arbitrary Docker, I mean it. Meaning we've, for example, spun up our like Postgres-like database running inside TE, right? So you can actually literally have a private state for your shade agents, on-chain agent, have private state running inside TE that you trigger, do some calculation, and the output becomes public on-chain or private off-chain, right? So like it's an arbitrary, like complex software that runs there. And so now you can have lots of these TE nodes that join the network. They will need to stake something to participate in proof of response. And so now you can actually have an ability when you send a request to prove that one of them is offline or not, right? So this gives you kind of this liveness guarantees from a network of verifiable nodes. And so you actually have a fully verifiable live cloud. Obviously, like if the node is offline, you need to effectively reroute to another node. So there needs to be a like additional protocol like for kind of load balancing the work, etc. But overall, this gives you kind of a verifiable cloud, something that, if you've been in crypto in 2018, everybody was promising you. This is actually it, offers effectively a system to achieve that by combining proof of response TE cloud, using blockchain, and then obviously leveraging chain signatures to go multi-chain.
Yep.
Okay. So if you're not bored yet, we have more stuff. So all of this is cool. The next level of this is the idea of intent. So intent is really more from a kind of user perspective and kind of higher level developer perspective. If I have some requests, right, and I actually don't want to figure out how it should be done, right? So this is like, hey, I want to rebalance this portfolio. I don't want to actually figure out exact, swaps that needs to happen. I want somebody else to do that, right? So you can communicate this request. So here you have some way of communicating. So for example, this can be centralized, running inside TE with verifiability. This can be our decentralized TE cloud, where this propagates. And so you have other parties, which can be either verifiable or not. So this can be some, like friendly face, and this can be some things that's running inside TE that can respond to this saying like, hey, oh, you want to execute this complex procedure, I will do it for you. And, this will cost you this much, and I'll do it in this long, right? So the simplest example of this obviously is, swap one Bitcoin for whatever, 100K USDC. Somebody's like, cool, I'll do it maybe, 99,500. Somebody's like, no, I'll do it for 100K. And the cool thing compared to usual blockchain, where you would submit this request on chain, and then effectively now everybody can observe it, and you have miner extracted value where people try to front run it. Here, because it's a private request, and you're actually getting the quotes, you're getting the kind of, hey, how much you would do it. So it's an interactive protocol, you choosing the best option, right? So there's no way to front run you because you choosing what's the best option going to be. And then you already submitting effectively two signatures, your signature and the solver signature on chain to actually set it, to commit to this outcome, right? Now, this protocol can be a bit more complex. There can be like some escrow time where, there may be dispute because, for example, you said, build me a building with 5 floors. It said like, okay, cool, it's going to take a year, and I'm going to do it for whatever, $5 million. And so this $5 million is actually going into escrow. And then if the building is not built, there's a way to resolve that and get the money back, right? So simplifying, but that's kind of allows you to have this complex off-chain negotiations protocol, figure out what you want to do, submit this, start executing and disputing. TE offers you like additional benefits because now, for example, who doesn't like launching new tokens? Well, you can actually launch new tokens inside TE itself. So you have new token on chain, so XYZ token. And so all of the XYZ token is owned by the account inside this TE. And so when people want to buy it, the TE is actually market maker, right? So you have a fully like confidential and also verifiable, you know exactly how it works market maker, right? So this can be as simple as, your Uniswap formula, or this can be as arbitrary as, have you tweeted today about this token, then you're allowed to buy, right? It can be arbitrary logic that actually runs here as a market making logic that actually responds to requests from users. So this actually solves one of the fundamental problems with blockchains where however you parallelize it, if people are trying, like if 10 million users are trying to target the same piece of state because everybody wants to trade Trump, it doesn't matter how you parallelize it, that piece of data is congested. And so this actually allows to have, you can arbitrarily scale this number of TEs that can respond to this request that control the supply. And so they can all effectively reply to different users. So you can actually have a scalable, market making, fully verifiable through the TE and replying to intents.
Yeah, I think the interesting thing here is it's not limited to trading tokens or swaps. It's more general, and it can be extended to things like commerce and just buying a laptop or whatever you want to do.
Yeah, so the example we showed, this is more going into ATP already, but yeah, you can say, hey, I want to buy headphones. Somebody's like, well, here's some options for you, right? An agent replied. You're like, cool, I'll select this option. Let's go to the process. We escrow the money, and then when the product arrives, right, we resolve it or dispute it if it didn't arrive, right? So this actually allows to do more traditional commerce in this way and general payments infrastructure. Think of credit card payments, but now done through those flows. And again, because you have guarantees, you can have guarantees on some of this other side as well. You can actually do a lot of new things in this way.
Yeah, it's also very flexible. You can do OTC and stuff like this. Still use the same framework to settle. And it's not just X times Y equals K.
Yeah,
very flexible.
This can literally have a Twitter whitelist. It can have an arbitrary formula of market making, etc. So, but it also can be any arbitrary AI code that runs whatever, right? So that's kind of the idea. Is we're effectively moving from trying to fit everything into blockchain to effectively have an EC2 level verifiable compute that you can then interleave with effectively like arbitrary requests and responses through this network. So on top of that, we build effectively the agent stuff where these agents are now communicating with each other. And so AITP is really just conglomeration of all these products, right? Where it allows effectively one party to initiate some communication, and then parties to exchange, structured data. Like, okay, I want, request some data from you. I want to request signature. So let's say this is agent B, this is agent A, and you have maybe like user. And so kind of the idea of AITP, you can have like multiple of these parties in the same conversation, and some of this gets replied directly by agent A, some gets propagated to the user. So have like a full flexibility of effectively decomposing intents into like any number of participants and kind of exchanging all this in one communication. But the cool thing is because it's kind of maintained, think of it as a thread or as an email thread, you can then, if something, like if you have a dispute, right, let's say product didn't arrive, agent didn't do the good job, you can effectively add like another dispute agent, for example, who joins the thread and like, okay, what happened here? Like, what did you promise? What's the process, etc. And this itself, can escalate to like court, because this has like a full like conversations logged as well that is only shared between these parties until new parties are joined. So kind of AITP effectively creates like this overlay over all of this to kind of on the like agentic level to kind of join all of these pieces together and enable them to trade, converse, and interact, as well as do business, do kind of transactions, exchange private data, UIs, and other parts. So point is, all of these pieces effectively working together. They all build on top of each other, and we're effectively enabling this vision to talk about like how AI is actually gonna be your interface through the through Web3 and Web2, and all of these pieces are really kind of powering that future.
Yeah, it's very exciting. And,
Yes.
forward
So still a bunch to build, but
Yeah.
we already see. I mean, you saw the demos. I think we have more demos actually. I don't want to show more demos, but yeah. All right, we're out of time. So it's time for drinks. Apparently, it's time for drinks. You probably need a drink after this, so yeah, I understand.
All right, Illia, Bowen, thank you so much. Yeah, ladies and gentlemen, as you have just heard, there's going to be a lot of booze, so you can go and get as drunk as you want to get. If you love that as much as I did, it will be on YouTube, it will be on Twitter, it will be on Facebook, it will be on OnlyFans, LinkedIn, Tinder, wherever the videos usually are. So you'll be able to catch up with that in just a few hours. But until then, please, if you could stand up, because we need to move the tables about and get like everything all sorted. But we are back here tomorrow, same time. Don't forget to register on Luma. Until then, goodbye. God bless. Have fun. Don't get too drunk. Bye-bye.